enter that number. It's recording. All right, we'll get started since it's 12:32. First of all, thank you so much for everyone for coming today, those who are attending online. I think this is one of our most well-attended seminars of the series, and so we're really happy to host Dr. Yet-Ming Chiang, who's joining us as the Coursera professor from the Department of Material Science and Engineering at MIT. He works broadly on energy storage technologies across various length scales, from the electronic and EV route to all the way to the grid scale. He's made a lot of significant contributions at the industrial scale, major contributions on lithium iron phosphate applications, semi-solid electrode development for manufacturing, as well as recent efforts in long-duration energy storage applications. He's a member of the National Academy of Engineering, a fellow of the Materials Research Society, as well as a fellow of the American Ceramic Society, and a member of the National Academy of Inventors. He has numerous awards, including the Electrochemical Society Battery Division Technology Award, the Economist Innovation Award, the World Economic Forum Technology Pioneer Award, among many more. But I just want to lastly highlight his significant contributions to co-founding or founding a lot of companies in the decarbonization and energy storage arena broadly, and probably many of you are aware of the American Superconductor Corporation, A123 Batteries, 24M Technologies, Desktop Metal, Form Energy, and most recently getting into decarbonization in industries related to concrete and cement, Sublime Systems. He's the co-director of the newly inaugurated Center on Electrification of Decarbonization of Industry, which is a significant and growing interest here within the Andlinger Center. So without further ado, I'll let Yet take over.
Thank you, Kelsey. Thank you, Kelsey. Let me make sure the mic is working. Mic is working?
Yes.
Okay, terrific. Thanks for that intro. I'm going to tell you at the end a little more about this new center that we're starting at MIT. The topic today is going to be mostly storage focused, and pardon me, I have to first share. Let's see. Share screen. And let me put it on full screen. There we go. Okay. I started working on batteries in about the early 1990s, and since then, we've continued to do research. But every once in a while, we do some research that looks like it has the potential for being spun out into a technology. Right? So I'm not going to spend a lot of time on the sort of battery research science aspects. I'd like to geek out on that topic as much as any of you. But what I'll talk more about is 3 examples where lab research made it into the technological world and to commercialization. And a little bit, 2 short stories on lithium ion and 1 longer story on the most recent topic, which is long duration storage, and try to explain what our motivations have been, twists and turns along the way, pivots we've had to make, and so how this process has worked. If we go back in the early 1990s when I started working on lithium ion batteries, that technology had just become commercialized at that point. Right? The first commercial lithium ion was in 1991. And so have had this opportunity to kind of watch the development of advanced batteries over nearly 3 decades. So the first, I'm sorry here. So first, let me just say a little bit about lithium ion phosphate. And it's what we did in this case, a company called A123 Systems. And people always, some people know and some people don't know where this name comes from. And so, what's this, alphanumeric, naming scheme you got here? And so it turns out that A sub 123 is a force constant. I'll show you that in just a second. But what happened in this case was that we actually started off doing something related to self-assembling batteries. Right? But in the course of identifying materials for self-assembling batteries, came across lithium iron phosphate as what was then a new cathode material that had not really made it into commercialization at any scale. And we ended up making batteries and building 6 plants in China, 2 plants in the United States, and in roughly the 2008-2009 timeframe, we started attempting to manufacture batteries here in the US. Right? This was a high-power lithium-ion battery, and the first product was a power tool. But today it's kind of taken for granted that electric vehicles are fast accelerators. Back then, the image more was of a golf cart, right? And that's what my friends used to joke with me about. Right? And so we did a number of things to show that these are high-power batteries. And 2008, Lewis Hamilton won the Formula One title using A123 batteries in the first hybrid system. Every lap, he could discharge once, and he got a lot of power out of that one discharge. Right? Passed a lot of cars. Right? So that application also branched out into things like this wind farm here. For several years, for nearly a decade, this was the largest lithium-ion battery farm on the planet. And this is in West Virginia, supports that wind farm over there. And even in Chile, this is an installation where these storage trailers, surprisingly, supported lithium mining, right, in the Atacama Desert there. And so I've always had this vision that in these batteries are lithium atoms that came from that site. And it's kind of like, salmon returning home to spawn. Right? And so mining more lithium. Right? All right, so this was the first thing, this adventure. And one thing we discovered was that this nanoscale lithium iron phosphate had exceptionally good life. And what was it about nanoscaling? Some of it was fairly straightforward kinetics. With smaller particles, you can transport ions in and out faster. But there also was an aspect of the fact that the storage of lithium in that compound involved the first order phase transition. It was a discontinuous phase transition. And in a lot of battery cathodes, that's a fairly destructive process. And in this case, when you went to very small particles, the phase diagram changed due to the coherency stresses. And this allowed a very good cycle life. And so this is just an example fairly early on. I think these cells actually eventually went to about 30,000 cycles. Right? And so I've done a field test since 2009. I bought this car in 2009, put one of our battery packs in it, 5 kilowatt hours. So 13 years later, 130,000 miles, about 4,000 deep cycles, right? And still going strong. And so my wife claims that the all-electric range has diminished. I don't believe that. But it's turned out to be a very good battery. Interesting thing is that at that time, this was a high-power hybrid vehicle battery, and it was considered to have too low an energy density for all electric vehicles. Right? But if you're watching the electric vehicle field develop today, you're probably aware that many cars, in fact, the majority of passenger cars are headed towards using lithium iron phosphate as the battery chemistry. Somewhat for reasons of cost, not really for reasons of power, but for reasons of availability, right? Which is tied to cost. So lithium and iron as opposed to other metals. Okay, so, but it actually started with a entirely different idea. So people used to ask us, what does A123 mean? You say, well, A123 means this. There's an equation, that's what it means, right? And so we actually started the company based on a concept for self-assembling batteries, where the cathode and anode would repel each other due to negative van der Waals forces, which only can happen between dissimilar materials. Right? And we actually, we wrote a paper and demonstrated that this could actually work, but we didn't think that it could work well enough in practice. So roughly, less than a year into the company's life, we realized that we were sitting on lithium iron phosphate, which is a very interesting material published on, and that we should pivot. So that was an example of a pivot. And we pivoted into lithium iron phosphate, and that's where we ended up. Right? Okay, let's see. That experience with lithium-ion battery manufacturing, I should say at this point, what eventually happened to A123? Well, A123 went into bankruptcy around, I think, 2010, 2011, because of the following phenomenon. We had built 2 factories in Detroit, or near Detroit, that had a capacity of 430 megawatt hours of battery a year. And not a gigafactory, approaching half a giga. And so, sounds like a lot, but the market simply wasn't ready at that time. The largest customer was Fisker Automotive. Their entire production over the entire life of that company was less than 1/10 of that annual capacity of manufacturing. Right? Power tools was fine, but when it came to building large EV cells, there simply wasn't enough of a market. It would be, I think, a very different story today. So eventually, the technology that was in A123 went out into 4 separate companies. The prime acquirer of the technology, Wanshan Corporation, is one of China's largest auto parts makers. The lithium iron phosphate business went to Johnson Matthey. The grid storage business, I showed you those grid storage trailers, that went to NEC of Japan. And then there was a defense and aerospace business which went to a small company in Michigan. So the technology kind of went forth, but the company didn't, right? One of the things I learned during that time is that the process of making lithium-ion batteries is arduous, complex, failure-prone, and has simply too many unit operations in series in which you can suffer yield losses at each point, right? And so I've often made this analogy that if you look at a lithium-ion battery, and the number of very fine layers we have, it's the equivalent of baklava, right? It's a very fine, so it's a bulk product, but it's made of thin films. It's entirely made of thin films. And in this case, these are sort of sub 100 micron films. And so the basic idea here is that in order to produce that kind of a product, you have this enormous complexity. And what it says at the top is that this is a process in which you take a paint, and you paint it on a metal foil, and you try to dry that paint, which is your electrode, as fast as you can without it cracking. Right? And then you process that coated layer. At the top of this plant, you see some plumbing. And that's how you can identify the coating plant, because it's a recovery of the solvent. And so one of the things that didn't make sense about this whole process is starting with something wet, taking you through a boiling process. And so, of course, that's an energy consumption that is undesirable. And then recondensing it to recapture that solvent, right? And so this wet to dry, and then at the end, infusing a liquid electrolyte again, that seemed like a unnecessarily complex process. So I had the following idea. What if we were to get around all of that and not make electrodes, and instead make electrodes that were, from the very beginning, a fluid, right? And so this was supposed to be a flow battery. And so I think there's a little animation here which shows how this is supposed to work. We showed that you could take battery, cathode, and anode materials and design a suspension which was electronically conductive, ionically conductive, would flow well enough, right? It wouldn't always jam the fuel cell stack. Most of the time, it would jam it, but you could make it so that it would work. And you can make a flow battery this way, and so here's some data for a lab-scale flow battery. So we thought this is a way to get around the entire manufacturing process, right? We started a company called 24M. Right? 24M is named after the concentration in molarity of a lithium-ion battery electrode, right? 24 molar. That's a very high concentration, you'll appreciate, right? But that's what we were able to do with these liquids. And so that's pretty cool, so we'll name it 24M. Right? So we pivoted again, though, and let me explain how this happened. A flow battery has a lot of attractive features, and probably many of you in the audience know these. You can decouple the energy storage from the power, so you have a lot of flexibility in how you design that. You have components that can be replaced. Importantly, you don't have to make coatings. You don't need a coating line. And we thought all of those were advantages. But when we sat down and did the techno-economic analysis, what we realized was that the cost benefit in building a battery like this, as opposed to building a regular battery, a stack battery, that was actually only a few percent, and probably didn't justify the complexity of the whole system. Okay. So that resulted in a pivot to a different way to use the same capability. And this is something called the semi-solid electrode. Currently, a lot of people are getting confused, and they say, wait, are you a solid-state battery or are you not a solid-state battery? I said, no, we're a semi-solid electrode, right? And it's a battery that's based on this electrode, which, if you hold it in your hand, feels like a damp dish rag, right? But what it is an electrode in which you use the electrolyte as the processing solvent. So you avoid that drying process. You don't avoid the calendaring process. You take actually something over a dozen unit operations and reduce to just a few. Right? And so this is the electrode, right? And over now roughly a decade, what 24M has been able to do with it is the following. It's a very simple casting process now. So you simply cast that electrode and it goes directly into a cell. Right? The cell is in the middle. This is a so-called unit cell construction. And that's actually a patented design there. And you can imagine that now assembling a battery, you simply take a bunch of what are now sealed a lot like playing cards and simply just stack all these playing cards together. A number of safety advantages because of that electrical isolation. Also because the electrode is literally softer. Right? And so this picture over here, that's a crushed cell. So those are cells that have been massively crushed in an edge crush test and never short-circuited. Right? So it shows that there's some benefit to softness. And then at the end of life, it turns out that there's some advantages into the fact that you can now just simply unzip the baggie, as it were. There's no binder used in here. There's no calendaring. Right? So when you have a lithium-ion battery in which the electrodes are all bound in plastic binder, you have little choice except to kind of shred the whole thing and recycle that. And here, we can actually just unzip the cell and take the active materials directly off the electrodes and reprocess those. So these are all ways that you can use this approach, and the cells work pretty well. Here are a couple of examples: a grid cell, 2,500 cycles, an EV cell using this NMC 811, which is the higher energy density of the NMC cathodes currently. And so what has happened here is that this was a process innovation, a manufacturing approach. And to get to scale, we decided after a lot of consideration that the best way to do it was to license it as broadly as possible to as many manufacturers as possible. Right now, there are 6 or 7 licensees. The most recent one announced was VW. Who now owns 25% of this company. But the first one was Kyocera, and they have their own manufacturing plant in Japan where they make these batteries based on this design for grid storage supporting solar panels, solar arrays. Right? So, okay, another example of a pivot here. So one of the questions that I often get asked as a result of having worked in lithium ion is, so looking forward, can lithium ion do it all? And now I want to turn to the story of grid storage. Right? And this is where I've been spending a lot of my time over the last few years. And so we all appreciate that lithium ion is a very well-developed and also rapidly scaling technology today. Right? It's embedded in our daily lives. But the problem that we need to address with the decarbonization of electricity is this one, in which from 2020 to 2050, these are all projections, but what this projection says is that solar and wind will grow. Nuclear doesn't show it growing. I actually hope it does grow. But solar and wind will grow, but we'll still have this base load. And coal will disappear, but gas will remain. If we quantify what this is 780 gigawatts, and we'll try to figure out, later I'll try to translate that into, well, how much storage do you need in order to take what is a renewable asset that's intermittent and turn it into baseload? Right? So we would say, okay, this is our ultimate goal in decarbonization of electricity. Right? Can we do it with batteries? Right? Okay, the kind of storage that we'll need in order to do that is variously referred to as long-duration storage or multi-day storage. So what is long-duration storage in a battery has gotten longer over time. Okay, so, whoops.
No, can I ask you a question?
Sure, please.
Can you go back one more?
Yep.
So this increase, is this a projection? Is this the increase in amount of electricity? Is that a projection for with assumptions about electrification of different sectors, or is that just assuming energy demand business as usual in terms of different sector uses of electricity?
I think we'd have to dig into the details of that BNEF report to answer that question.
Okay, so
but
it's a critical question
yeah.
given what we need to do in terms of decarbonization of the.
That's right.
Of
Yeah. Well,
sectors.
I will eventually try to translate this to something on the order of 100 terawatt hours of storage, but I'll allow allow me a factor of 2 error in that. Right? Okay. But thank you. I'm afraid I can't answer that right away, but we can look into that again. So this is here's an example of long duration. So it used to be that someone would show up and say, we want a battery for long duration applications. How long do you want it to be? So we'd like it to be 4 hours. Okay, today what long duration refers to is really multi-day. And so this is all 365 days in Texas in 2021. And I'm not sure my pointer will work here, but you can see up here where there are these gaps, especially in the top row there, January and February, where it's multiple days. Right? Okay. This next slide shows historical data, 2019, 2020, Upper Midwest and New England. And then model data, these are from my colleagues at Forum Energy for 2050. And the basic message is that multi-day, what we need are multiple days. Right? Now, there's an argument that eventually you might need an entire season. Now, if you're in Antarctica, you get sun half the year and none the other half the year, right? So that's clearly, but for most of what we need, we'll need multiple days, maybe a week, 2 weeks. So I'm going to use that as a target, and I'm going to round that off to roughly 100 hours. Okay. So what do we need in order to do that? There are a lot of ways of describing the cost targets for long duration storage, but I'm going to use the simplest one possible here. I mean, we could get into duty cycles and a bunch of other things and energy throughput, but I'm going to try to simplify it to just this very simple equation where we have the cost of a natural gas plant. And I'm going to call that 2,000 a kilowatt. Right? And if we are competing against natural gas, which is that a couple of slides ago, what I indicated, and we need to store for multiple days, and we'll call it 100 hours, 4 days here. Right? Very simply, just the balance of the dimensional balance tells you that what you need is about $20 a kilowatt hour. Right? Okay, this is the installed cost of a battery system. Right? By comparison, lithium ion for the grid is coming down somewhat, but for the grid, there's a cost adder over an EV battery pack today about $75 a kilowatt hour. And so we're in around $250 a kilowatt hour for lithium ion grid installation today. Right? And so this clearly shows the gap of roughly an order of magnitude in cost if we're going to do this with a battery. Right? Okay. So next the question of how much storage does this really translate to? Right? And I have 2 data points here. One is an analysis done at the MIT Energy Initiative. Right? And the second is a recent report from late last year from McKinsey and the Long Duration Energy Storage Council, a trade organization. Right? And they come up with 2 numbers, and the first number here is 100 terawatt hours, and you see some of the assumptions that go into there. First, there's an estimate for the US, and then multiplied by 10 for the world. Right? And then the McKinsey study says 80 to 140, so I'm going to round it off to 100 terawatt hours. Right? And so what does 100 terawatt hours mean? It's not a unit we deal with in our daily lives. So one way I think we can think about it is that if in the year 2050 we have 10 billion humans on the planet, right? This would mean that every 10 people have a battery somewhere supporting their electrical needs. That's the size of a Tesla Model S battery pack. Right? So that's what this scale means. Right? 100 terawatt hours worldwide. Right? Okay, so, and most people react to that as, okay, that seems not crazy, right? That you might need that amount of storage. Right? So, what are the constraints on lithium ion then? Can we get there with lithium ion? Right? And also in that last slide, you probably saw that we could double that number if we take into account the EVs that we're going to build over the same period of time. Right? So maybe it goes from 100 to 200, right? But it's of that magnitude. So this is a busy plot, so let me explain what it shows. References are down here from my colleagues at MIT Energy Initiative, Elsa and Bob Jaffe. And so the CAGR on the vertical axis is the compound annual growth rate in production of that metal, mining and production of that metal. Right? The histogram over here is over the time period that you see here, what were the annual CAGRs? Right? So year by year, how much the production decreased. In some cases, it shrinks. But in this case, you see that the most lithium production ever increased in a single year was 10%. Okay. If you're going to reach 100 terawatt hours by the year 2050, this is what the compound annual growth rate has to be. And what you see is that in the case where all of the lithium that you mine, it all goes towards batteries and there's no other consumption, you need to have, well, 10%. And you might say, okay, that maybe we could do that. But keep in mind that this means that you have to have 10% a year, every year for the next 28 years. Right? So that kind of indicates how heavy a lift it is. The resource limit is over here. So what this chart shows you is that it's not actually that we don't have enough lithium. It's just that the production has to scale at a pace that's very demanding. Right? So now, you can be bullish or not about the rate of increase of lithium mining and production, but this at least illustrates how much it has to be. Each of these curves is 100%, 50%, 25%, how much of the new lithium goes towards the battery. Yeah, right? And then the width is just simply different battery chemistries. This is all NMC. 811 and 622. 811 has higher energy density, a little higher voltage, uses a little bit less lithium. That's what that means. Okay. So this is a complicated plot, and I'm kind of pausing here because I'm going to now show you two more just like it. Okay, so, all right, cobalt and nickel, same idea. Histogram on the lower left, what's the CAGR, the production over, historically for each of these metals? What does it have to be to reach that 100 terawatt hours? And again, you kind of come to the same conclusion for cobalt, is that, yeah, there's a precedent that there was 10% in 1 year, but now we have to do that over 28 years, nonstop, in order to get to this kind of target. Right? And nickel is a little bit easier, right? But still a very significant lift. So the overall message here is that if we were to do it all with lithium ion, we may have actually enough of each metal, but the amount of production is daunting. And so I actually assume that for grid storage, neither cobalt nor nickel will be used in the long term. It'll be something like lithium iron phosphate, maybe a manganese-based chemistry. But as long as we do it with lithium, that previous chart will apply. Okay.
Are the origins of the lithium, cobalt, and nickel all coming from mining in this assumption, rather than recycling? Any role
yes,
for recycling?
these are all from mining, and
Yeah.
the recycling question is a good one. And so I would say, how much can recycling help us out? And I think the simple answer is that when you have this exponential growing trajectory, recycling is not going to help you out for a long time. Yeah. Okay. Yeah, but good. That's always a good thought. How much can we recover? Right. So, okay. So what's the outlook? So that was those were the metals. Now let's think about actual pack production, cell and pack production. And we all know how much lithium-ion costs have come down, but they've come down dramatically over the last 3 decades. We're now in the the sub 200 range, where we argue over, is it going to get to 60 or is it going to get to 50? Right? So 3 decades, massive cost down. The growth in production goes from where it started in 1991, and this is from 2020 to 2030, right? And the compound annual growth rate in production is about 20% over this decade that's being projected here, okay? Now, this vertical scale is in gigawatt hours, so at the top here is 2.5 terawatt hours, right? And so this projection says that over this decade, we're going to get to 2.5 terawatt hours a year. And so there, to reach 100 terawatt hours by 2050, again, you have to have this scaled production rate, this CAGR that's pretty daunting. Right? We have to keep this up for now the next 28 years too. Right? Okay, all this is saying, well, lithium ion, to meet all of our storage needs for long duration storage to decarbonize the grid, it's going to be used. I have no doubt that lithium ion will be widely used, EVs, short duration storage, but it doesn't look like it's going to solve our problem. Right? Okay. So what else can we look to? And I want to make sure, do a quick time check here. We're 1 o'clock. Right? All right, I'm going to try to move just a little bit faster here. So I talked about lithium ion, and this is a plot that shows the cost of energy versus the cost of power. And this is a trajectory that describes essentially what you need. So if you have a long discharge duration, you're discharging at, by definition, low power. And so if you have a relatively high cost of power, that's less painful than if you have a very high cost of energy. Right? And the reverse is true. If you have a very high power requirement, what you want is to pay less for the energy, pay less for the power, but you can afford to pay more for the energy. Right? And so this is a way of looking at different technologies. In this Future of Energy Storage study, which actually is the official launch of this study, which has taken 3 years for us, is going to be next Monday. Right? But so as we look at this, these are some of the options. I'm going to pretty much skip over redox flow batteries. And on that side, there are several possible competing technologies. I don't have really time to talk about all of them, but I could potentially address it if there are questions at the end. I'm going to talk about metal air batteries. Right? And the reason for this is the following. This is a plot that we first conceived of back around 2017 as a way of looking at battery costs at the chemicals level. And so the argument was the following. We're going to define something called the chemical cost of a battery, which is the cost of the cathode, the anode, and the electrolyte. Right? Can't store energy without those 3 components. And so you take the cost of those 3 components in the right stoichiometric ratios, the right adjustment for the amount of electrolyte, and you calculate that cost divided by the amount of energy that you can store with that combination. Right? That, because you haven't added any other components, you haven't built the battery, right? That's not the whole battery cost. It's a floor on what the battery cost is. Right? It's the lowest, it's the cheapest the battery could ever be. Right? And by year, what we plotted up were all the battery chemistries we knew of at the time. And so there's an updated version of this plot that will appear in the report I just mentioned. And when you look at this and say that our all-in cost is about $20 a kilowatt hour, which is the second line up there, what you realize is that only those chemistries that are way below have a chance of meeting these needs. And in fact, why not just go to the lowest that you see here? Right? And so the lesson here was that as long as you can use air as one electrode, air is still free, so there's obviously you're saving some cost there. You don't have the materials cost of whatever that electrode is, and it's going to be the positive electrode. In low-cost inorganic, sodium, sulfur, iron, used with air is going to always give you the lowest cost of stored energy. Right? So that's where that thought process leads you. Right? And what we originally started with was under the Joint Center for Energy Storage Research, or JCESR, which is a DOE hub. It's based at Argonne. We started working on this corner here. And we developed several variants on what was intended to be a room temperature sodium sulfur battery. High temperature sodium sulfur has been around since the late 60s. That battery has very low chemical costs, but it's a high temperature system, and by the time you're done building the system, it's over $1,000 a kilowatt hour, right? Okay, maybe 800 today. But if you could do it at room temperature, our thought was that, well, we can really take advantage of that low cost of sodium sulfur and do it at room temperature. And so the first idea is a complicated, what appears to be a complicated chemistry here, but it's not as, well, okay, it's complicated. So I'm not going to try to go into all the details here, but it's a flow battery, right? And it has a catholyte and an anolyte. And the anolyte here is a polysulfide solution. And then the catholyte here is something that uses oxygen, but does not directly use oxygen to oxidize or reduce the sulfur itself. Right? So so what we have here is an alkaline side and an acidic side, it turns out. Right? And so this device has a very low cost of chemistry. So over here on this plot, you see the cost of chemistry here. And as a flow battery, you can calculate the cost additively between the power stack and the tanks. And so depending on the duration over which you're running this battery, the cost will decrease here. Oh, excuse me. The cost will decrease as you go to longer and longer durations simply because you have less stack and more of the tank. Right? And so it asymptotically approaches what the chemical cost is plus whatever the tanks cost you. That's the idea of this plot. Right? So this looked like, for long durations, is a design that could have the potential to reach very low cost. You see it approaching $10 a kilowatt hour here. And what you see plotted up here is the data points are compressed air and pumped hydro storage. It looked like it might be competitive with that. Right? So this looked exciting enough to us that we said, let's try to commercialize this. Okay, so one of the things we discovered along the way in looking at this battery is that something that anyone who's worked with air-breathing chemistries knows is that they tend to be inefficient because the oxidation reduction of air has a high potential, is a inefficient process. So if you look at the cell voltage here versus charge and discharge, you quickly see that this is only about 50% round-trip efficiency. Right? And so that was concerning, except that when we did the modeling on the impact of that, in a world of very low-cost electricity, the cost of delivered electricity, this is levelized cost of electricity here on the vertical scale, right? As a function of efficiency, if let's say you went from 80% to 55% efficiency, it would only cost you about a penny a kilowatt hour. Right? So that was interesting because it told us that efficiency was not nearly as important for these long duration storage systems as it is for something like a high-powered lithium-ion battery. And so that was a critical piece of learning because it told us that air-breathing chemistries could have a future in these kinds of applications. Right? Okay, well, I'll tell you what happened. I mentioned that you need an acidic side, acidic electrolyte, and an alkaline electrolyte. And when it came to commercializing this chemistry, we found that that materials challenge was a really difficult one. It basically required invention of a membrane that could be a single ion conductor for sodium, but could at the same time separate a strong acid from a strong base. Didn't take us very long to realize that that's a really, that's a big materials challenge, right? And so, but the idea of the parameters that one would need to meet for this kind of storage were still there. And so we turned to metal air systems. Right? Again, air breathing, again, very low cost. But now instead of using sulfur, which is very abundant, let's use a metal, which is very abundant. Right? And so metal air batteries have also been around for a long time. And you can read this faster than I can say it to you. But basically, if you have anything that it's a metal, or let's say even silicon, if you can oxidize it, you can make a battery out of it. But relatively few of these are reversible or rechargeable batteries. Right now, I would say lithium, zinc, and iron are the only ones that really are rechargeable metal air chemistries. Right? And so this is the chemistry space that we look at. And one of the problems is that these all have relatively low round-trip efficiencies. Right? But what I made the argument in the last slide that that is not a showstopper. Okay. So iron air, let's talk about iron air. It's pretty apparent why iron is attractive, and I'll talk about that a little bit. So the iron air battery is really a battery in which you oxidize or rust the iron in the process of discharging it, right? You have to remember, for the non-battery geeks amongst you, if you want to try to remember which direction is discharge, it's always what is energetically downhill. Iron loves to rust, so rusting the iron is the discharge step, right? Charging the battery is the unrusting of that iron, going back in the other direction, and reducing that oxide or hydroxide back to the metal, right? Okay. A couple of the interesting requirements that come into play in order to make a functional iron-air battery. If you think of the air electrode, that's like the lung of the battery, right? The iron is oxidizing, reducing, and the air electrode breathes in and exhausts oxygen, so it's a lung, right? Now, our lungs are so-called bifunctional. You both inhale and exhale. It turns out that to make an iron-air battery work, it's desirable to have two electrodes, one to inhale and one to exhale, right? So you have essentially two lungs, two oxygen electrodes. The green one is the oxygen reduction electrode that takes in the oxygen. The gray box is the oxygen evolution electrode, that's the exhale. So that's how this design works. What you form is iron hydroxide, you see here, FeOH2. And at deeper discharge, you can also form an iron oxide. But that process turns out to be much less reversible. Okay. So mainly, you're trying to use this first step here. And so here is a full cell using an alkaline electrolyte. This is what a typical charge-discharge curve looks like. I'm going to point out again here, look at the voltage on discharge versus the voltage on charge. And so right there, you have a round-trip efficiency. You can see that's going to be about 50%. Right? The second is that if you look at the capacity, you see that you're putting in, the charge line is longer. You're putting in more electrons to charge it than you're discharging it. Another source of inefficiency. Right? And so what's that coming from? That's actually coming from the fact that the iron electrode, the HER, hydrogen evolution potential, is pretty much the same potential at which you want to charge your iron electrode. So that's one of the challenges in this chemistry, is that when you charge the battery, at the same time, that iron electrode also wants to produce hydrogen. Right? And so, this is where a lot of the engineering and design and chemistry comes in. Right? And so these are, I'm being very upfront, these are the deficiencies of this system. But, for the long storage duration applications, it all still works. And so this is the history of the iron-air battery. There actually has been, over the last decade or so, a lot of work, including from Sri Narayan's group at USC, who spent a lot of time on this. There was earlier work targeting applications for which this really is a terrible battery, like an EV battery, right? It's the EV applications, right? And so then there's one other piece to this, which is the discovery that there's a particular form of iron which really makes this iron-air battery sing. Right? So how do we make steel today? Well, we make steel by first making iron in at least the electrical process. And so what you see here are pellets of something called direct reduced iron, or DRI. Right? So it's referred to as DRI in the industry. And these iron pellets are the lowest cost metallic form of iron. And here is an example of a large battery module that stands about this tall, about 4 feet tall, which uses these pellets in an iron-air battery module. Okay. So this is how iron is produced today. Direct reduced iron is the stage at which we take our iron ore pellets and reduce it to metallic iron. So if we want metallic iron as the starting state, this is the place to grab it. Okay. And that's what Form Energy is doing with this entire approach. Okay, back to this plot. Iron air using DRI is even lower cost on here. That's where it sits. Okay, all right. Let's talk about the scaling. Can iron air do it? Think about it in the same way that we did lithium ion. This is a Nucor iron plant in Convent, Louisiana. So, field trips are wonderful things. And here you can see, those dark gray piles there? You know what that is? Those are all iron ore pellets coming in to be reduced. and then shipped out by boat. This is this is on a riverway, obviously, to ship things in and out. But you see the numbers up here, right? The CAGR in iron production to meet that 100 terawatt-hour goal by 2050 would only, actually, not even 2050, just 10 years, that would be less than 2%. The reason being we have this giant steel industry for all the other reasons we use iron. Okay. All right. I don't want to give the impression that iron air does everything. The ideal scenario, this is a cost minimizing model, still would have, this is power versus time, still would have short duration storage in there, slotted in there. You see those yellow shapes, that's lithium ion, right? That's the cost minimizing combination. Now, you could not use those and just build more long duration storage, but it'll cost you a little more, right? But I think that there continues to be a role for both short and long duration storage here. And there's one other connection here. There's an interesting synergy taking place now between what's going on in the steel industry. Iron is today reduced, those plants that I showed you, is reduced using natural gas. But for both that and later stages of steelmaking, there's an evolution towards hydrogen. Right? And so where are we going to get that hydrogen? If it's green, it's going to be produced probably electrolytically. Right? And so there's a synergy here between clean steelmaking and long duration storage in which we use that iron for this process. Right? All right. I'm telling you a story which comes from a team. These are my co-founders, all in this picture here. Form Energy, I told them I was going to give a talk down in Princeton, and they said, you have to do some recruiting. Right here, we're hiring. Right? The company today has about 200 plus, approaching 300 employees. It's trying to hire another 200 employees within a year. Right? And so if this area interests you, right, and well, all you have to do is go to that website and you can see all the job openings that are available. Recruiting is one of the biggest challenges for Form Energy today in order to get to that scale that we want to get to as soon as possible. Okay. All right, how much time do I have? 5 minutes, perfect, all right. Okay, this is just commercial traction. 2 commercial projects announced. Great River Energy, Upper Midwest, incidentally, near the so-called Iron Range in North America, where our iron comes from, and Georgia Power, one of the larger utilities in the U.S. Okay, I think I'm going to skip this summary because I've pretty much said it all. And I just want to spend the last couple of minutes talking about a new initiative. This, again, recruiting. Right? I'm going to spend my last couple of minutes here recruiting for a new initiative that we've just started at MIT called the MIT Climate Grand Challenges. We have a new center that's just started called the Center for Electrification and Decarbonization of Industry. With this very low-cost electricity that we all anticipate that we'll have, we can store it and use it like I just described, or we can use it for other purposes. And this is really directed towards the following. What we've done here is create a center which was down-selected over a 2-year process. We're one of 5 flagship projects. There were initially 100 proposals, now down to 27 full proposals, out of which 5 were selected. And so we're one of that initial 5. And it's intended to tackle these 4. These together constitute 15% of all human emissions of CO2, and almost half of all industrial emissions. So if you take the industrialized world, just these 4 is almost half of it. It's 45%. Right? They're roughly in rank order like this. Actually, I think these last 2 are flipped. But cement, steel, ethylene, and ammonia. Right? And so the idea, what we're trying to do is to develop electrically based processes, a lot of which will be electrochemical processes, in which you can synthesize each of these materials and decarbonize through the electrification route. Right? And let's see, my particular passion in this part is cement. And at some other point, maybe I can tell you more about what we're trying to do in that area. But Kelsey mentioned it at the beginning. Right. So I'm going to stop here, and I hope I've left enough time for some questions, if there are any. Right.
So I think we'll have some microphones going around. I see one question already there.
Exciting talk, Yet-Ming. I really like that the last slide, the green manufacturing and decarbonization. And we actually submitted a proposal to NSF for the Science Technology Center involving 8 faculty from MIT. If we are invited, I'm going to call you. Thank you very much.
Some of those 8 may already be part of our project. We have roughly, we have about close to 20 faculty who have expressed interest.
Someone's in the back. Yes.
Hi. So one of the major advantages of lithium ion, at least in grid applications, is the ability to kind of change the duration. So like you could build a half-hour battery or a 10-hour battery. Do metal air batteries, or I guess iron air batteries, offer that same kind of design flexibility?
Yeah, I'm glad you asked this question because, one of the things that you'll read in the news today about long-duration batteries is this wonder that we have a 100-hour battery. And, I always say, if you're a battery engineer, you just think, or even if you're not, you think about this for a moment, I have a 100-hour battery. This is a 100-hour battery. What's the big deal with a 100-hour battery? You can take any battery and discharge it over 100 hours. It all goes back to that equation that I showed you. Can you discharge over 100 hours and still meet a particular cost target? Right? And so lithium-ion batteries, because the cost, at least in this grid scale, grid installation, it's about $250 a kilowatt hour. If you want to be able to deliver electricity, store and deliver electricity at the same cost as natural gas, you're limited to about 4 hours. Okay. I think there'll be a cost down, so I put the outer range at 8, maybe even 12 hours. But 100 hours, that's why it's too expensive. Right? But to answer the second part of your question, no, an iron air battery at a 4-hour discharge interval is not a good battery. Polarization will be pretty enormous.
So, Yet-Ming, that was great. I just want to take a moment to make sure that people here know that I just want to thank you, Yet-Ming, for being part of our community since the beginning, the Andlinger Center, because he was someone that I asked to be on the very first executive committee to make sure that we got headed in the right direction. So I want to thank you for that. And it was interesting about your last slide because part of what I am embarking on now here and part of why I came back was, in fact, an initiative very similar to that will be joint between the Princeton Plasma Physics Lab and Princeton. And so we'll have to talk more about that.
Terrific. Yeah. Actually, I wanted to say something about being part of this community. When I first was invited by Emily to join the External Advisory Committee, there were a number of meetings, and this building had not yet been built then. Right? And one of the enduring messages, I learned that there's such a thing as, it's either called University Gothic or Collegiate Gothic architecture from the architects. And what was fascinating to me about it was that, then as now, universities don't always have as much money as they'd like to have. And so to build buildings with lower cost materials at the time meant that you used limestone instead of marble. Right? So limestone was, I think of it as the drywall of its day. And so I learned that there was such a thing as collegiate Gothic, of which there's much around Princeton. And this center was designed to harmonize with that architecture. Okay. Right? So
it was a really good memory. Listening to Ron.
It was a lot of fun when the Andlinger Center was being stood up. Yeah.
Any other questions? I think we have one here.
Thank you for your presentation. I'm wondering, would you care to comment on the liquid metal batteries that are coming out of another MIT group, specifically for long-term storage and cost comparisons with yours?
Sure, yeah. I think that, so first, maybe for the rest of the audience, I'll just describe what it is. It's a concept where you have 3 liquid layers, and they're organized by density. Right? And so if you have an electrolyte that has an intermediate density between a cathode and an anode, then you have a self-assembling battery. Right? And we thought about density-based separation when we were working on self-organizing batteries back in the day as well. I think so. It's been over a decade, and I think what has shaken out from all the possibilities in the periodic table is that currently the preferred combination is calcium and antimony. Right? And we did take a look at that in our future storage study, and so antimony is on the list of critical materials. It is resource constrained. I think that there certainly could be some application of that, but I don't think it can tackle this 100 terawatt-hour challenge. Okay, that's the sort of the brief answer I would give you. Yeah.
How you think about the lithium battery and sodium battery in the future? Thank you.
Oh, I'm sorry.
What do you think of sodium batteries?
Yeah, lithium and sodium batteries. Thank you.
So that's a great question. I pointed to lithium as potentially the limiting element. Sodium-ion batteries, usually you give up a little bit in voltage. Right? On a pure sort of cost of energy basis, it seems that by going to the more abundant material, the gain in cost, or the reduction in cost, is not that significant. Right? But yeah, I would say that if sodium can do what lithium can do, and of course our resource of sodium is vastly greater than that of lithium, that's another direction in which this could go. That would help answer the mineral supply question. You still have the scaling of production question, which is the other point that I was trying to make about how much we'd have to scale lithium ion, or in this case, sodium ion production, in order to meet that kind of the 100 terawatt-hour goal.
So I'm just going to ask one last question to end. So you started off with this anecdote of why 24M couldn't overcome the challenge because of the lack of an EV market in, say, 2010. And so we see parallels with that potentially with recycling right now. But what can policy or the government play in alleviating these challenges and accelerating the adoption of technologies that we need, even though the market's not there?
Yeah. Well, I will tell you that one of the most painful things to experience back in the mid-2000s when we were growing A123 was to see every car company developing an EV preferentially using batteries produced in their home country if they were available. There was one exception, one country that was the exception, that was the US. Okay? So there was never a serious consideration given to requiring that a US car maker for what were at that time the very first plug-in hybrids, plug-in hybrids, and EVs would actually use a US battery maker. Right? So yeah, there are all kinds of, that's a fraud issue, right, as we all know. But I think that in order to reach these targets, what we're seeing now is at least a different atmosphere and a different language around domestic production. That's one of the reasons why iron is so interesting. So iron is, well, it's on every continent because it's below every continent. Right? The Earth is just one big, ball of iron. But we have historically had iron production in the U.S. It's easy to see or to understand that you would not be constrained by overseas resources. Where we are, one of the really interesting things about the move towards manufacturing of iron air batteries is that as you look to where you might site a plant, right, you look for a waterway. Right? The stuff is heavy. Right? You got to ship it in, you got to ship it out. And so all the really interesting, attractive manufacturing sites seem to be located in the middle of the country on the Mississippi or some tributary off the Mississippi.
Well, also where you're refining the iron to begin with. Just have an industrial cluster.
That's right. So yeah, and yeah, I mentioned the Iron Range, and that historically, the upper Midwest has been where our the local iron has come from. Right?
All right, in the interest of time, let's thank the speaker one more time.
Thank you.